Okay, so we're going to talk about population and community ecology, and it's a really dense chapter with a lot of different concepts and ideas, and we're just going to jump right into it. So, nature exists at several different layers of complexity, from the individual to groups of individuals, populations operating together. Number of different populations of different species form communities, and these are in turn nested in different ecosystems, which finally, coalesce together into the total living layer of the planet, the global biosphere. So some terms just to get us started, sort of the currency of this study: population ecology, study of different factors that cause populations to increase or decrease, population size, total number of individuals within a defined area at a given time. The density is a little more specific. It's the number of individuals per unit area at a given time. And distribution is how individuals are distributed over that area with respect to one another. The population sex ratio, of course, is ratio of males to females. And in natural systems, that can be wildly skewed, where you have fish species that are dominated by mostly female individuals, few males. Same in bird populations as well. It can be the other way as well. And then you have population age structure, which is how many individuals within a population fit into certain age categories. And then factors that may influence the increase or decrease of populations: certainly natality, just making new offspring by birth, hatching, germination, cloning. Fecundity is a measure of the physical ability of an organism to reproduce. That correlates with fertility. It's basically a measure of the number of actual offspring produced. And finally, mortality, or the death rate. Okay, when we look at distribution here, population distribution, how individuals are distributed, you can have three sort of main scenarios and then gradations between those. So you have clumping distribution, uniform, and random. And so uniform distribution looks like this. Individuals are spaced relatively evenly. And then you have sort of a random dispersion. This is real common in many tree species, or things that are broadcast, seeds that are broadcast by wind or water currents. And then clumped distribution is going to be, aggregates of individuals, such as schooling fish or flocks of birds, mammals, small mammals that have colonial nesting situations. So examples, again, trees tend to be random in their distribution. A lot of seabirds will be uniform, especially nesting on these islands where their space is limited, and they want to maximize the use of space, but also minimize competition with other birds in the area. And finally, clump distribution is here at the bottom, and this is going to be things like meerkats, and again, different flocking birds, things like, flocks of ducks or geese, and certainly schooling fish. Okay, factors that influence population size. So there's density dependent and density independent factors. And of course, density dependent factors are going to be things that depend on the factors that influence population survival that are related to density. And so things like, the spread of infectious diseases or stress or predation, those are going to depend, and the effect of that is going to depend on how many individuals there are in a given area. Independent factors are going to be typically weather related or climate related or natural disaster type situations, things like severe storms, earthquakes, volcanic eruptions. They're going to have an impact regardless of the density of the population. So, here, a big cold snap may increase mortality, in humans, and it's density independent. It's going to, affect people regardless of how closely packed they are. Density dependent is more like an infectious disease like Ebola, and it's going to spread more rapidly in densely populated urban centers. Okay, we're going to look at some growth models. So growth rate of a population is just the, the number of offspring an individual can produce in a given amount of time, and the relative, rate of reproduction of the population. The intrinsic growth rate is under ideal conditions, no limits, what would be the maximum number of individuals that an offspring could produce or population can produce. And then, of course, in the real world, population growth is affected by competition, number of different factors, abiotic and biotic. Okay. Oh, and biotic potential, of course, is if there were no limits and no factors kind of curbing population growth, what would be the sort of maximum size a population could reach? That's the biotic potential. Okay, so exponential growth model is a J-shaped curve. It's just exponential growth of a population. So it's going to, ratchet up rapidly. Humans on planet Earth are undergoing exponential growth. We may be slowing slightly, but it's still exponential. And so we look at a J-shaped curve for humanity. What happens to most populations over time is that they run into limiting factors or limiting resources, the slow population growth, and ultimately populations bump up against something called carrying capacity, which is the total size of a population that can be supported indefinitely over a long period of time, given all the resources, food, habitat, water, shelter that are available. Okay, and so that leads us to the logistic growth model. So, initially it's going to be exponential growth, but then as the system or the population reaches carrying capacity, the growth rate will tend to slow down. So here you have this S-shaped curve. So initially J-shaped, and then as you run into the limiting factors or get closer to carrying capacity for that population, the population growth rate will tend to slow and stabilize. And humans on Earth are starting to just turn this corner. It appears to be that way, at least for now. Okay, so biotic potential and environmental resistance determine the carrying capacity. So here's biotic potential here. There's this early period of exponential growth. Then the population hits its carrying capacity and may go up and down depending on environmental factors that may be conducive for growth for a period of time, and then sort of work against growth, be negative for a period of time. And this can be things like climate, disease. So you can have this phenomenon called overshoot, where a population can go wildly above the carrying capacity for a short period of time, but there's always going to be a correction and a die-off, and the population will drop back below carrying capacity. And there may be kind of perturbations of that, over a long period. And you can see this with things like predator-prey cycles and simple ecosystems. Canadian lynx and snowshoe hare have a really close relationship. And so you can see here the hare is in purple, the population size, and the lynx is in light blue. And as the hare population increases, the lynx population also increases because it has more food available. And as the lynx eat lots of the hare, then the hare population will crash, and that will then cause the lynx population to plummet as well. And so these two go up and down together with some synchrony. Okay, here's this idea of overshoot. So you have reindeer on St. Paul Island, a big population explosion. The reindeer grazed most of the lichen that was available, and then they had a period where basically many of the individuals starved, and the population decreased dramatically. And then in theory, the lichen would recover, and as the lichen recovered, then the reindeer or the caribou would recover as well. Okay, just another way of looking at that. Now, we have different reproductive strategies. So you have K and R selected species. These are just general strategies. K species are going to be things that reproduce, not very frequently, tend to be large mammals, and tend to take care of their young during the early period of development, lots of parental care. And so humans are K selected species. And when that contrasts with another strategy for reproduction, which is R selected, which is going to be organisms or individual populations, species that broadcast their gametes or their seeds wildly all over and have no parental care whatsoever, and may create 300,000 offspring in a season, knowing that only a tiny fraction of those are going to survive to, not necessarily knowing, because we're talking about tree species or oysters, or tend to be mostly invertebrates or plants. But a small percentage of those actually survive. So again, R and K, rabbits are kind of more, there's a spectrum here, right? So when you look at this, there's R at one end and K at the other, and rabbits are not exactly in the full end of the R, like all the way to the R end. They're more really closely more in the middle. 12 offspring per year. Most mammals are going to be somewhere closer to the K zone or toward the middle. And then things, again, like invertebrates and plants are going to be more in the R. I mean, this oyster is 500 million offspring in the course of one single year. Okay, R characteristics: short life, rapid growth, early maturity, reaching reproductive maturity very early on in their lifespan. And little parental investment in individual offspring. Whereas contrast that with K strategists, they have high parental investment in the offspring, high parental care. They take care of their offspring sometimes for long periods of time, like 18 to 20 years, and tend to have fewer large offspring and really, really nurture those offspring. Okay, and then they finally follow the survivorship curve. So when you look at, you look at K strategists, that most of the individuals are going to tend to survive the early part of their development, and then, you'll have mortality events later in life here. So this is, maturity, and then, kind of as the whales and large mammals get older, they tend to die off. Whereas our strategists, most of the mortality is going to happen early, and only a few individuals will make it to adulthood or reproductive maturity. And then again, small mammals tend to be somewhere in the middle on the spectrum, and they're going to tend to have mortality all the way through their life.